Now let's talk about parity, uh, parity of these elementary particles, the lepton number and baryon number. And let us start with parity. And as we understand that this, what is this parity? Parity is basically, it's a mirror symmetry. It's a mirror symmetry. Or we can also call it, left-right symmetry or space inversion. These are proper words to illustrate this parity. Now, in classical mechanics, what we have under parity transformation, suppose I have R and if I change this R to minus R, so under parity transformation, this R is changed to minus R, and what it does is that the right-handed coordinate system is changed into the left-handed coordinate system, as we understand, and vice versa. And but in quantum mechanics, I mean, every moving particle is basically associated with a wave which corresponds to a wave function psi, and this psi it depends on the coordinates x, y, and z, and this we have a wave function psi, and this wave function depends on these space coordinates. Now, the parity of the wave function, this wave function, what it refers here is, it refers to its behavior under simultaneous reflection of space coordinates. I mean, reflection of x to minus x, y to minus y, and z to minus z. But the point is simultaneous. So the parity of this wave function, it demonstrates its behavior under the simultaneous reflection of space coordinates x, y, and z. Now the point is that so now if the sign of the particle wave function, suppose we have a wave function psi of x, y, and z, if its sign does not change, if it does not change after the reflection of this space, after the reflection that we demonstrate here by x, replacing x by minus x, y by minus y, and z by minus z. Now, in this case, what we say, if there is no change, then we say that the wave function has even parity. We call it even parity. So what is it? It's an even parity. So how would I like to demonstrate it in some interpretation? So parity, P for parity of psi, x, y, and z. And if I get the psi by replacing x by minus x, y by minus y, and z by minus z, here I have even parity. I have positive parity. Now, on the other hand, if the sign of the particle wave function is changed under the reflection of the space coordinates, then the wave function, the wave function has a odd parity, or we can call it negative parity. So here we have positive parity. And if I have, under similar transformation for a wave function, x, y, and z, if I have minus of psi, minus x, minus y, and minus z, then what I have is I have odd parity. I have odd parity. Or we may also call it as negative parity. Negative parity. That should be the point. Now, if this parity operator P is applied 2 times on a wave function, then certainly the wave function should translate back to its original form. So if I have to, if I write down, if I take the parity of psi as x, y, and z, suppose it comes out to be minus psi of minus x minus y and minus z. Now, if I take another parity, so p raised power 2 psi of x, y, and z is going to give me the p of what? It's going to give me the p of this minus psi, minus x, minus y, and minus z. And what should we obtain from here? We should obtain psi of x, y, and z. So from this, what I can say that this p square is 1. That means this p square is plus minus 1. Now, if p is plus 1, I have even parity. And if this p is minus 1, I have odd parity or negative parity. For p plus 1, I have positive parity. Now, talking about baryons. Okay, baryons, what are baryons? In baryons, we have nucleons, we have lambda, we have sigma, we have chi, and we have omega, and all of these particles, all of these baryons, what they show is positive parity. Baryons show positive parity. So when you take the reflection of these particles simultaneously, there is no change in the sign of the wave function. So baryons fall in this category, and their antiparticles. So you have the antiparticles of baryons. All of these antiparticles have negative parity. Negative parity. That means they have odd parity. They have odd parity. And talking about photons, mesons. What mesons does? Mesons have positive. They carry positive or negative parity. Photons and gluons. They carry negative parity. Now, parity is conserved. Parity is conserved in strong, and so parity is conserved in strong and electromagnetic interactions. Electromagnetic interactions. It's an important point to be noted. So this parity is conserved in case of strong electromagnetic interactions and strong interactions and electromagnetic interaction, while parity is not conserved in case of weak interaction. So parity is not conserved in weak interactions. So we should say here that the charge, the charged bosons, like we have W plus, minus, and some neutral bosons like Z0, they have no fixed parity. They don't have any fixed parity. No fixed parity. Now, talking about the parity of composite state, system of particles. This is equal to the product of the parities of its constituent particles. If you have a range of particles, and if we have to calculate the overall parity of that system, all we have to do is to multiply their parities to get the overall parity. Thus, parity is multiplicative quantum number. So that's an important point. So parity is multiplicative quantum number. Now let's go with lepton number. Okay, lepton number. So that's L. Now, to distinguish between various elementary particles of the lepton group or or family, these particles are assigned a characteristic, and that characteristic is called as lepton number. I mean, all leptons, all leptons, E minus, pi negative, tau negative, nu E, and nu pi, and nu tau. These particles, all of these particles have a lepton number. That lepton number is +1. On the other hand, all of their antiparticles. So what are their antiparticles? So we have E plus, we have pi plus, we have tau plus, and we have nu E bar, we have nu pi bar, and nu tau bar. All of these antiparticles, the antiparticles of leptons, what they have is they have a lepton number of -1. So all other particles except the leptons have lepton number equal to 0. So any other particles not falling in the family of leptons, their lepton number is always equal to 0. So what should I say? I should like to summarize it. So what I have, L is +1. It is +1 for leptons. And L is -1 for antileptons. And L is 0 for all particles. For all particles except leptons. So this is our lepton number. Now let's talk about the baryon number. Now we have baryon number, and this is B. Now the concept of this baryon number or nuclear charge, it was introduced to characterize the elementary particles of baryons, of the baryon family. Now all the baryons, we have proton, neutron, lambda naught, sigma plus, we have sigma minus, we have sigma 0, and we have chi, and we have chi minus, and we have chi 0, and we have omega minus. They are all baryons. And what am I going to say here is that all of these baryons have a baryon number B, and this B is equal to +1 for all of these baryons. And all of their antiparticles, I mean, all of the antiparticles of these baryons, so P bar, N bar, and lambda naught bar, sigma plus bar, sigma minus bar, sigma naught bar, chi minus bar, chi naught bar, omega naught minus bar. These are all the antiparticles of baryons. All of these baryons have a baryon number equal to -1. And this B is equal to 0 for everything else other than that of the baryons. So if you talk about the baryon number of leptons, that's always equal to 0.